This is part 3 of lecture 8 of LEC 5300. We're going to start talking about Bayesian estimation. And Bayesian estimation extends the idea of maximum likelihood estimation to incorporate the idea that we have some knowledge about reasonable values of the parameters in advance. So to motivate that, let me give you an example. So if you recall from our discussion of the maximum likelihood estimation, when we looked at the Bernoulli random variable, which is like a coin flip, either achieves values 0 or 1 or tails or heads, with probability x is equal to 1 or heads is equal to mu, then if we want to estimate mu, the probability of heads, remember that we came up with the result that the best estimate of mu is the sample mean. Now because the xk's are either 0 or 1, then we can say, well, if we just count the number of times that 1 appears, that's the sum of all the xk's. Right? So if we call that number m, the number of times we observe 1, and divide that by n, that is the maximum likelihood estimate of the probability of heads mu. Now suppose that we perform an experiment, we have a coin, we flip it 3 times, and we observe 3 heads. In that case, the maximum likelihood estimate is mu is equal to 3 heads divided by 3 trials, or 1. Right? And so if we were going to ask, well, what is your best guess of the probability of heads based on the data you've seen, your answer based on maximum likelihood would be 1. Right? But intuitively, this is somewhat uncomfortable because of the fact that that implies that if we took this coin based on just 3 coin flips, my prediction would be that if I flipped this coin forever, I would always get heads. Right? And so it seems, well, maybe there's some chance that it's not 1, so how could I take this kind of thing into account? And so the idea here is that we haven't really taken into account any prior knowledge about the mu. So for example, we might assume that in advance, if you were going to ask, well, what do you think the values of mu would be, maybe you'd say, well, it's probably uniform over 0 to 1. That one might be some idea that you might have in advance. And so it seems like, well, in that case, you wouldn't come up with this answer that it would be 1 for all time. So the idea of Bayesian parameter estimation then is to combine information from the training set D, right, the same thing we did in maximum likelihood, but now we add prior information about the parameters, which is assumed to be expressed in the terms of a distribution P of theta. And so P of theta is going to be a distribution that tells us what are the likely values of theta and what are the unlikely values of theta. So then the goal then is to estimate a density over the feature vector x based on the training data. So what we'd like to do is get the probability density function of x given all the training data and the prior probability distribution over the original parameters theta. Now, in order to do this, it turns out that the really critical step is to estimate the probability distribution over the parameter theta given the data. Right? So we already have a probability distribution over the parameters here, but we're going to somehow modify that based on the data. Now the reason that this is the critical step is because once we have this, we can easily compute the probability density function over x simply by integrating over all possible values of theta, where we weight the distribution f of x given theta by the conditional density of theta given d. So here we assume that f of x given theta and d is just f of x given theta. Right? And so that seems reasonable because the distribution only depends on the parameters theta. So if I know the parameters theta, then it really doesn't matter what d is, because d was just obtained by sampling data from this probability distribution. And so theta is really the complete knowledge about the things that will generate x. Now, by Bayes' formula, we get an idea of how we might be able to estimate the probability distribution of theta given d. We simply say, well, we're going to switch the order of conditioning, so we're going to put d on the other side, so we get f of d given theta times f of theta divided by the integral of f d given theta, f theta d theta, right? So here we're just multiplying f of d given theta times f of theta. This kind of gives us, if you remember Bayes' theorem, this thing gives us f of d and theta, right? And this integral here, because I'm integrating f of d and theta over theta, this whole thing is f of d, right? So the probability distribution function of theta given d is just f of d and theta divided by f of d. So I can write this in this way here, and the important thing to remember is that the d here, the f of d, is really just a normalizing factor. It doesn't really depend on theta. And so in order for me to figure out what's going on with theta, I really only have to look at the numerator. And this is really just something to make sure that when I integrate over theta, I get 1. So in order to do this, we need to somehow express our knowledge in terms of a prior distribution, f of theta. Now mathematically, it is convenient to use a form of the prior distribution such that when I take the posterior distribution by multiplying the prior by the likelihood, hopefully these two probability distributions, which are both over theta, look similar to each other in the sense that they have the same functional form, but maybe only differ by parameters. And so really what would happen in that case is that given this data, I have a certain set of parameters determining this distribution, and then once I have the data, I get a new distribution that has the same form, it's just those parameters have changed. And so we give this distribution here, f of theta, a special name if it allows us to do this, and this is called the conjugate prior. And it turns out that, well, because the likelihood has a different form for different probability distributions, the form of the conjugate prior depends on the assumed distribution. And just as a review, this f of d given theta, under our assumptions that the data is generated independently from the distribution, is just the product of the probability distributions of the individual data. Okay, so in the following we're going to take a look at some intuition about this problem, and then in the next part of the lecture I'll actually go through some numerical examples. So let's go back and look at this idea about the Bernoulli distribution. And in that case, what we had the thought was that, well, maybe initially, if I'm trying to estimate mu, so mu might be the probability of heads, I might have an initial guess about what the probability distribution of this one might be. Maybe I might guess, well, f of mu might be uniform over 0 and 1. So if this is mu, I have a uniform distribution. And what this says is that, well, the probability of heads has to be between somewhere between 0 and 1, and really I have no idea what the value is. It could be, you know, this one or this one. So all these values are equally likely. Right? Now suppose that I get a piece of data. Right? I flip the coin once and I observe, well, I got heads, or x1 is equal to 1. Right? Now what I'd like to do is say, well, now given that, what's the probability distribution function over mu, given that I know that x is equal to 1? So what I want to do is take this and say, well, what's f of mu given x1 is equal to 1? Right. So this will be a probability distribution over mu. Right? But now that I've seen a 1, right, then I know it's definitely possible for me to get a 1. Right? So there's no way the probability of heads is equal to 0. So that then suggests that the probability distribution of f of mu given x1 is equal to 1 should be 0 at this point, right? Because that's impossible. I've ruled that out by observing a heads. And because I've observed a heads, it seems like it's more likely that the probability distribution of mu is skewed more toward larger values of mu than to smaller values of mu. So if I look at this, I say, well, maybe it has to start from 0. It should get bigger. So what's the simplest function I can do that will go from 0 and get bigger? Well, it's probably going to be a triangle. Right? And this value here would be 2, just to make sure that the whole thing integrates to 1. Now, suppose that I flip the coin again, right, and I observe that x2, the second time I flip the coin flip, is a 0. Right. So now I want to know, well, what is the probability distribution of mu given that the first coin flip was 1 and the second coin flip was 0. Well, now that I know that I can get both a 0 and a 1 from this distribution, I have definitely ruled out this, right, because I got a 1. And similarly, I've ruled out this because I've gotten a 0. And now I've kind of got an equally balanced set of 1s and 0s, and so in that case you can kind of think, well, maybe what I should have is I should have the most likely guess to be somewhere in the middle, because I've got an equal number of heads and tails, 1s and 0s. And so I put the maximum value here, and then you can say, well, what kind of function would go up like this and then come down like this? You might get a triangle wave, but it turns out that actually what you get is a quadratic. Right, so this is like a parabola that has its peak value over here. Now suppose that I observed a new function here, a new data point. x3 is equal to 0, let's say. So we observed another tails. You can say now in this case here, the probability distribution function of f of mu given x1, x2, and x3 are equal to the values of I observed is probably now skewed more toward the 0 side, right? So rather than being kind of equally distributed to the left and right of 1/2, I would expect it to be more toward the 0 side of 1/2. So I might expect something that kind of looks like this, right? Again, I know it's definitely 0 here and 0 here, and so maybe the peak value here would be shifted over up to this point over here, which is a little bit to the left of 1/2. And so this is the basic idea, and what we'd like to be able to do then is see whether we can actually formulate this idea mathematically. And so we'll do that next time.